cool. Yeah, well, we can do notes for like 20 minutes, and then if you guys have questions or stuff you want to go over, we can go over that. I'm not allowed to let you leave before the class is supposed to end because I don't have any power, and I will get in trouble if I do. So hopefully you guys are fine with that. But yeah, anyways, so kind of picking up where we left off yesterday with complexity analysis and stuff. This kind of becomes a big deal the more you get into computer science when you're looking more at different algorithms and stuff. It's very important to know how those algorithms are going to affect your machine, basically, that you're running it on. Obviously, all computers have different hardware. The nice thing with Colab is you guys don't have to worry about your hardware. Google handles all that stuff for you because it's done in the cloud. But in later terms, like the Colab doesn't really exist for every possible programming language that you're probably going to have to use. So knowing how your results could be affected based on the input that you're giving an algorithm or some program that you're running can be really important. So yeah, basically time and space complexity. Time is how much time does it take to run, and space is how much space is it taking up in your computer. In Python, if you run, if you call a function recursively, like call a function within itself and don't set a base case, you'll eventually get an error in Colab or in any other Python IDE where you've basically run out of memory. And that's because your computer doesn't have the space to keep storing all these values you're telling it that it needs to store because they're important. So algorithms with very high space complexity, you need to have very kind of beefy hardware system or hardware and storage systems to deal with. Otherwise, you're just going to lose the data that you're trying to store and trying to work with. Comes in like space complexity and time complexity. Yeah, a bigger deal the more kind of in-depth you get into algorithms and stuff, but yeah. I mean, nowadays we're generating more data than we actually have the capability to store, like every second, basically. So, like, looking at your space and your time complexity is really, really important, and that's how you can, it's generally regarded as a very good metric, or an important metric to determining how good an algorithm is the efficiency of both of these complexities. Make sense? Cool. So, yeah, kind of a example of how time and space complexity would work. If your list has 10 things in it and you're looping over the 10 things, it'll take 10 units of time, one per thing. Same for 100, same for 10,000 or 10 million. So yeah, at the end of the day, if you're doing a linear search and you're searching over a list with n things, it will take n units of time and it will take n units of space to search through that list and do a linear search. Okay. Pick a number. I'm going to need to probably pull up a calculator for this, maybe. Hopefully not. Okay. Does someone want to pick a number between 0 and 100, or 123, 1023? Okay, we'll do you and then you can go. Yeah.
714.
Oh, don't tell me. Probably should have said that. All right, your turn. Okay, pick a number. Okay. Okay, 500, higher or lower?
Higher.
Okay, 762, higher or lower?
Lower.
Okay. 628, higher or lower?
Lower.
Okay. 564, higher or lower?
Higher.
586, higher or lower? Lower?
Higher.
Higher, okay. 604, higher or lower?
Higher.
615, higher or lower? 620?
Higher.
25?
Yeah.
Okay. So obviously that was kind of scuffed, but the idea is every time, the idea is you can pick any number between 0 and 123. There's 124 numbers because 0 counts as 1. So this is called a binary search, where you essentially are, if I pick a number between those numbers and between you guys you all pick a number, if by you guys telling me if it's higher or lower, I can immediately discredit half of every number on the other side of the number that I initially guessed. So me starting at 500, probably should have started at 512 because that's right in the middle. If you're going to write an algorithm to do this, it would do the math a lot better than I can in my head. But you would start at the middle point, higher or lower, and you essentially just knock off half of the possibilities at a time. So instead of doing a linear search through, like, if you guys had a dictionary and you're trying to find a word that starts with M, like, would you start at the start of the dictionary and go through all the A's, then all the B's, then all the C's? Obviously not, that's ridiculous. You would just pick up the dictionary, say, okay, well, M's roughly in the middle of the alphabet, I'll start in the middle. And then you decide if you need to move left or you need to move right. That's all a binary search is doing. You're starting roughly in the middle, and then you're immediately discounting half of the thing you're searching for something in. So if you're trying to find the word music, and you open the dictionary to, like, metronome, you know you need to go right just a little bit, and you just kind of keep going right until you've gone too far, and then you can go back left, and you kind of just bounce back and forth. So the cool thing is, binary search, because of that, like, removing half of the things you have to search through at a time property, actually becomes a lot more efficient at searching than a linear search. So the caveat with binary search is your data has to be sorted. And that's a whole other problem, which also takes into account time and space complexity. So linear searches are nice because you don't have to sort your data. You can be searching for a student in a class, and if the students are unordered, a linear search is a better option than a binary search, even though a binary search technically on paper is a better searching algorithm. Does any of that not make sense? Cool. And yeah, like, you can extend, like, the 1023 can extend to kind of any arbitrary number. I think as long as it's 2 to the power of something, you can do it in, like, 10 or 20 or 30 guesses. That probably isn't 2 to the power of 10, but it's, yeah, anyways. There's some correlation between, like, the largest number you can guess up to and the number of guesses. Oh, cool. Well, here we go, the magic behind the binary search that I've kind of already explained a little bit. But, yeah, so basically, yeah, should have started at 512, but, yeah, you can immediately discredit every number on the other side of 512. So you know it's either between 0 and 511 or between 513 and 1023. So that's the formula for it if you guys would like to know it. That's basically what binary search is doing from, like, a mathematical, like, equation point of view. But yeah, like, linear search can only check it only eliminates one number or one element in a data structure at a time, whereas a binary search will eliminate half of the remaining elements in a data structure at any given time. So you go from 1024 down to 512 to 256 to 128 to 64, 32, 16, 8, 4, 2, and 1, getting you the number that you guys would like to pick. So yeah, with linear search, as you probably have figured out by now because we talked about it for probably an hour and a half, the relationship is linear. If you increase n by a certain amount, it's going to take, if you increase the length of the list you're searching through by X things, it's going to take n plus X units of time and n plus X units of space per element to search through that list again. So yeah, like if you double the size, it now takes twice the amount of time and twice the amount of space. With binary search, because you're halving the amount of things you have to search through every time, it actually turns into base 2 log of n for the time and the space complexity, which is kind of cool. It's a lot more efficient if your data is sorted. So sorting is a whole other thing, which I think is actually a topic that comes up after this. But yeah, that also is, you'll deal a lot with time and space complexity when it comes to sorting, because when you're sorting data, you don't want it to take forever, because if it's taking forever, then you're kind of like, what's the point in sorting it if you're using binary search and that's taking like log base 2 of n time to find the thing you're trying to find, but it takes you 2 to the power of n units of time to actually sort all the data in the first place. Though all the work you're doing with binary search is kind of redundant when you could just do a linear search through it and you'll probably find it quicker. So there's some really neat and kind of smart sorting algorithms you can use. There's also some really dumb ones and some kind of interesting ones, I guess, as well. But yeah, the more general your algorithm is, typically the worse the solution gets. And the more you know about the structure of your problem, the better you can build an algorithm for it. It's kind of like you guys writing your assignments. You want to read the problem first. You want to make sure you understand the problem in this class or any other class. You want to understand the question that's being asked of you so you can accurately answer it to the best of your ability. So yeah, algorithm analysis and stuff is basically just a fancy way of saying solve a problem. And then, yeah, obviously there are other programming languages aside from Python. So the cool thing with algorithms is even though the algorithm or the languages that algorithms can be implemented in will differ, sometimes quite a bit, all algorithms are exactly the same in terms of what they do and how they are structured. So with the pseudocode for a linear search, because you guys now know how to do a linear search, you can probably do them with your eyes closed. You can do that in any language as long as you're familiar enough with the language to be able to write a linear search. So part of the objective of 161 is to get you familiar with some of these like intro level concepts that you will be using throughout the rest of your like programming or computer science like life cycle, I guess. But yeah, obviously linear search in Python, linear search in Java. You guys, I think James probably went over these in lab or maybe in lecture at one point with you guys. I remember bringing it up in lab once. But basically, Java is going to be the programming language you guys will be using primarily next semester in 162. And they're like the Python linear search and the Java linear search are doing the same thing. There's different weird syntax, like why does, like haystack, why does it have brackets here? That's just because it's an array. In Java, and most programming languages aside from Python, when you use square brackets, you're actually initializing an array and not a list. Arrays typically come in a fixed size, and lists in Python are actually made of arrays, but they'll increase their size by themselves without you guys having to tell it, okay, well, you run out of space, now add more space. So lists in Python will automatically increase their size, whereas most other programming languages don't do that. It's up to you guys to tell it to do that. But the gist of it's the same. You have a for loop. You have a for loop. All this for loop is saying is take an integer I, have it start at 0. As long as I is less than the length of the haystack, increment I by 1, and then check if the haystack indexed at location I is the needle that we're looking for. If it is, just return true. If you get through the entire for loop, which is denoted by these lovely squigglies, if you complete the for loop without returning true, you know you haven't found the thing, so just return false because it isn't in the haystack. And yeah, I mean, this stuff at the front is kind of how you define a function in Java. This just means it's a public function and that it's returning a Boolean. Don't quite remember what static means, so I'm not going to attempt. Actually, here, why don't we just look it up? Neat. Okay. Well, I don't have a lot of experience with Java, but it sounds like it's this linear search function is kind of like just a function in Python that isn't in a class. Yeah.
Okay, how come with Python, but the rest of them have those squiggly brackets that are kind of just on their own lines, and why?
Yeah. So Python uses indents to separate. Python uses the indents to kind of tell you what things are where. So if you move this outside of the for loop, I mean, you're going to get an error. I guess you should put pass in here. This is now telling you that you will you'll run the for loop until everything that's been indented once after the for loop is complete, and then go to the next line. Whereas in Java, you can also, like, it depends on how you like to set it up, but you can also have it look like this. So this for loop encompasses everything in these brackets.
Okay.
So that's like Python uses indents instead of the squiggly brackets, just for kind of easier readability. Like, obviously looking at this with just indents is a little bit nicer than looking at a bunch of squiggly brackets. But yeah, it's just a different way to kind of display how the code is written, and what is encompassed in the things that you're trying to do. So in like a loop, you'd have one set of squigglies. If you have an if statement, you would have like the if haystack at index I is equal to needle. If it is, then run everything in these squigglies, and then just exit the squigglies and keep going. Does that make sense? Mm-hmm. Yeah, cool. You can also, if you really, really wanted to, make your code look really not nice.
Or you can stick it all in like one line.
Yep. And the super fun part of this is that will run, and it will work perfectly fine because it's separated. Everything in here is separated correctly by the squiggly brackets. Never do this, please. I'm sure you guys can all figure out just by looking at it that it's kind of horrible. But I digress. Anyways. Cool. So yeah, Java uses squigglies basically instead of indents. The reason that there are indents in here is just to make it easier to read. These indents don't mean anything. They don't affect how the program runs. The only thing that'll change how it runs is the squigglies. C#, kind of the same thing as Java. Pretty similar, almost one for one, actually, I think. Yeah. Neat. Yeah, C#, just a different programming language. Also uses squigglies. Oh, also, fun thing with most languages aside from Python, at least like Java, C++, like kind of more commonly used ones, I guess. most lines that aren't if statements or like loops or function calls have to end in a semicolon. It's a way to let the compiler that is running the code know this is the end of the line, now go and do the next thing. You're probably going to run into a couple of errors with just forgetting to put a semicolon in. I still do, so hopefully you guys don't have as much trouble with it as I do. But yeah, C# also semicolons. C++, a little bit different. Instead of having public and static at the front here, we just have bool, so that just tells us that it returns a boolean. You have a vector that holds integers, basically a data structure kind of similar to a list or an array, called haystack, int, needle. Vectors have a method called size, which we implemented last class for the course class. So which will just take the length of the haystack, and same thing. C, same thing pretty much, just slightly different syntax. But the thing here is the linear search never changes. The only difference is the way that you're implementing it. So implementing it in different languages has no effect on the actual algorithm itself. Now, obviously, with slightly more complex algorithms or programs or really big data sets, it's generally going to be slower in Python because Python is typically a slower language. Python holds your hand a lot more in terms of stuff it does in the back end, whereas C++, Java, C#, you kind of get a lot of free reign over what you want to do, especially with reference to like pointers and lists and stuff like that. A lot of that kind of falls on you to make sure that it works, and that all the stuff in the back end is happening exactly how you think it is. Python lets you kind of skip all that and just lets you go to just writing code. So that's something to think about too. Like James has an undergrad student in this fourth year who's doing his thesis, who's kind of refactoring code that James wrote years ago in Java for basically taking a problem and performing symbolic regression. So taking like a bunch of points and trying to find a mathematical function that fits those points. And he was asking James if he could do it in Python and would it be better. It isn't better one way or another to do something in a particular language. Different languages are designed to perform different tasks. Python's a lot more geared towards data visualization, data analysis, and machine learning, whereas like C++ is really good for software design. It's fast and it's very easy to find the things that you want to change and change exactly only that thing. You can still have side effects, but it's a lot easier to manage them if you know what you're doing in C++. Yeah. But yeah, anyways, James is an undergrad student that's doing his thesis this year. Basically, it comes down to Python will run it slower, even if the code that James wrote in Java is one for one perfectly implemented from Java into Python, just because Python tends to be a slower language because of all the backend stuff that it does. Java runs quicker and can do a lot of stuff, but Python's kind of been becoming a lot more popular, especially for kind of performing data science tasks and creating visualizations based on like Excel files full of data, which is kind of cool. So like the visualizations you guys would have done in assignment 2, the code that James wrote that you guys could run to let you show the infections of cities and the histograms and stuff, like you guys would be able to do that. You could randomly generate like a NumPy or like a list of values, or you could take an Excel file and you can just plot everything on like just on a plot basically, and like that's kind of one of Python's strengths. But yeah, it is slow. Anyways, yeah, really long ramble just to say Python slow, Java fast. They have upsides and downsides to both of them. So most of the time, well, not most of the time, all the time, the algorithms always stay the same. The only impact and the thing you guys will have to think about it later down the line would be what language am I implementing it in? What are the strengths of this language, and what are the weaknesses? And how does that actually affect the runtime of the algorithm itself? Because the algorithm might run, if you give an algorithm 10,000 things, it might run twice as fast in Java than Python, but it's probably just because you implemented it in Java and not Python. Haskell. This is a fun language that doesn't let you use loops, so everything has to be done recursively, and that is the code to do a linear search in Haskell. I have zero experience with this, so I might mention it to James if he wants to talk about it, or like if anyone wants to talk about it in lab, feel free to bring it up. But James could go through this line by line and tell you exactly what everything's doing. I just don't have any experience with it and probably would get something wrong. So I'll leave that to the expert. But anyways, I guess, yeah, we're around halfway through class. Does anyone want to go over anything specifically from the course before like the exam? Like, are there any topics that people are like maybe hazy on, or just want a quick refresher, or I can just keep talking at you, I guess, if you like. Yeah?
Maybe like F strings and the backslash tab and like
Okay, yeah.
string stuff.
Okay. So that obviously is an empty string. This has now become an F string because it has an F in front of it. F strings in Python are really, really good for formatting. I think that's what the F stands for, but I wouldn't quote me on that because I'm not 100% sure. In F strings, you can have a variable, and it can be, say, a value of 10. If you take a regular string, or an empty string, and this has like number of students today, and you add a variable to it, and you print a string. You guys have probably figured out by now that's going to give you an error, because you can't concatenate ints to strings. So the way around this, and the way that you can work with data where you don't necessarily know the type but want to output it in some way, is with F strings. So by converting this to an F string and kind of removing all the other stuff, so we now, the base string we want to use every time and we want to print out is always going to be the number of students in class today. So, actually here, maybe we could rename this to number of students. Yeah, cool. So the number of students in class today is the number of students. So, running this, even though we didn't change we didn't change number of students, this is still an integer. It allows the integer to be concatenated and to be placed into the string between these curly brackets, or the squigglies, because this is an F string. If we remove this, and it's no longer an F string, it just prints exactly what you have in the quotation marks or in the definition of the string. So, yeah, if you have it like this, and let's say I counted wrong, and there is maybe 21, 22 people here today? 22, sure. So it lets you change, it lets you work with data that isn't necessarily a string, and you don't have to worry about like calling string of number of students and then add that to a string and do string building like that. So it allows for a much more efficient kind of for much more efficient string building, and it lets you kind of get a sense of what your output's going to be before you even have to print it. So if you ever wanted to put, for whatever reason, the number 5 here, you could have it formatted like that. where you would say, okay, take the value of num students, place it one space after the colon, and then after the whatever value num students contains, one space after that, place this stick, one space after that, place the number 5, and then give me that string, and then print it. So the value of num students is 22. You could change this to a ridiculously stupid number, and the same formatting still holds, no matter what size of the number is. Does that clarify and help a little bit? Sweet. Does anybody have anything else? Yeah.
Opening and closing files.
Yeah. Oh, that's fun. Okay. Oh, I don't know if there's a text editor here. Shoot. How do we? Okay. Yeah. Yeah, we can do it with the random CSV files I have here. So, there's a couple of different ways you can open and close files. A very common one that, like, if you guys are Googling, how do I open a file in Python? You can have the file name be sample data slash, and let's do California housing. So this in here is just the path to the file. So it just says go to sample data and then find the file called California Housing Test CSV, and that path to the file then just becomes the file name. So with opening the file as a file, print a file dot line. Yeah. See what that does. Shoot. There we go. Cool. So also, whenever you open a file, close it. So we'll be using this file like in this loop, and after the loop, what we're going to want to do is just close the file. So we're opening the file, and we're assigning it to the variable a file. A file becomes like a file reader object that you can use to iterate through files line by line. So why don't we do an f string? And we can put all of this into a lovely string, and then we can put a \n after it, and run it again. And all of that is on one line, which is fun. Is that all that's in that? Nope. Oh. Let's read lines. What does that do? Aha! It makes us a list. Lovely. Perfect. Okay. So I lied. Maybe don't do it exactly that way. So once you have opened your file and you've given it the thing to call it, you can then loop over. So you can loop over every line in a file. So the read lines method gives you a list of of length n, where n is the number of lines in your file. Every element in the list will just be a line, basically. So we can loop over all the lines with read line, and then print every line one at a time, and it's going to give us a bunch of latitude and longitudes and a bunch of other values depending on what is actually in this file. This is really big. Cool. Let's get that back up to the top. Lost 5,000 lines. Well, I guess we can open the file back up and look and see what the header was. So by opening so basically line 2, you're opening the file and you're saying with this now open file as a file, loop over every line and just print the line once. Another way you can loop through a file is by instead of using with open as, you can specify you can assign the open file name thing as so you can assign the object that's returned from open file name as a variable, and then just loop through B file like this. Print line, and then close our files because closing files is important. You don't want to be writing or adding things to files. So this is just when you're reading files. So there's also another parameter you can put in open, which tells you if you want to read or you want to write. If we wanted to, we should call this something else, write file, equals, November, what day is it, 23rd? November 23rd. And so we're going to write things to a text file. Right. Hi. So when we run this, it should, if I know how to write it properly, create a file in here. Maybe not. Maybe I don't know where they go and call that. Let's find out where the files go. But where? Go in there. Oh, it's fine. Maybe go to the main disk. Okay, well, anyways. Yeah, so you can open files doing you'll probably see the with open a lot more frequently than this kind of more janky way. The with open's just nice, it keeps everything indented, letting it just basically be easier to read. But we can take this and we can open. Oh, that's why it didn't work. Because I actually, okay, oops. I didn't change the name. Okay, let's see if that works now. Nope. I want to go back. Nope. So let's delete that and we'll run it again. So we're going to open a file called November23rd.txt, and we're going to just write hi, and then we're going to close it. So if we run this, and maybe sync that, cool. November 23 pops up, and it's written hi. So we can then, I guess, go through. Now that November 23 exists, we can open it. Oh, I already had that done here. Whoops. Anyways, we can open specifically November23.txt as a read file, or read file, and then we can read the file that we're reading, take every line, and then print the line. And if we do this, oh, didn't close it. But yeah, we're going to write hi to a file, and then we're going to open the file and double check that that's what we wrote. If we wanted to write, here, I'm going to change this so it's a bit nicer. Oh. Write file as C file, sure. Anyways, if we wanted to write something, so I guess we can write, so for I in range 20. We can write every number from 1 to 20 to the file. Dot write, and then we can do I, and we can close it, and then we can open it again and print the lines. Now, this is going to return output that's probably not what you would want it to. Oh no. Oh, right. That was meant to be a string. It is a string. It's fun. How do they do it? Oh, right, didn't specify. Okay. So I think the default parameter for the second one is always going to be read. If you do not specify write and then you try and write to it, it's going to tell you that you can't write to the file because you didn't ask it to write to it. But if we run this again, hopefully working this time. So we took a range of numbers from 0 to 20, so 0 to 19, and wrote them all to the file, but they're all appearing on the same line. We need to specify that we want to create a new line at the end of every. We want to specify that we're going to create a new line every time we write to a file, or it's just going to add it on to the first line, basically. So if you run this now, it's going to print everything out on a new line. Cool. Is any part of the reading and writing the files confusing? I know you guys will have to do that first time before, so if you have any questions, speak now or forever hold your peace. Cool. Anyone have any other questions? Everyone knows, like, if statements, everyone understands loops. Cool. All right. Well, I mean, yeah, happy Wednesday. You guys are good to go.